Well, greetings everyone. This is our third workshop in a row in the module Scientific Data Manipulation. We are moving from basic data inspection and data cleaning towards some more, let's say, slightly more advanced techniques. And on today's, let's say, menu, we have topics on outlier detection and time series, time-based indexing. Okay, we will start immediately. So the first part is outlier detection. So we can shortly describe what does this term mean. So what is outlier? So outliers are some values that are initially strange, either large or small compared to the rest of the data. And in real-world data sets, that they may represent some measurement errors or sensor malfunctions or maybe mistakes when entering data, inserting data in data sets. But they also can represent real values, but that values are really rare. So they don't happen frequently. And our job as data scientists is to determine whether we want to keep these values in a data set, or we should do something with them, either remove it or replace with some more meaningful data. So why do outliers represent problems? So all modeling algorithms that we will later use, for example, machine learning algorithms to make some predictions or make some classification or clustering, are sensitive to outliers in data, especially the ones who that calculate some distances. For example, k-nearest neighbors support vector machine, or in regression, linear regression or logistic regression, and many similar algorithms which calculate some distances from the existing data are sensitive to outliers, because those distances can then be large and then can have really big influence on the operation of the algorithm. So the algorithm can make some skewed predictions or classifications or decisions because of those outliers. Surely, if you have a small percentage of outliers, they shouldn't influence your data so much, but it is your job as a data scientist to first determine whether you have, or maybe you suspect that you have some outliers. And then when you determine that you may have outliers, you have to decide what to do with them. So in today's workshop, we'll first learn about the techniques on how to first inspect the dataset to see if there is actually some outlier in the dataset, and to use some default state-of-the-art, let's say, techniques for quantitatively determining whether there are outliers in a dataset. And when we learn how to do that, then we may argue what choice should we decide, what should we decide with those outliers. So we will start as in previous workshop in a similar fashion. So we will first import the libraries. Okay, I shared with you the workshop. So again, we will be using Jupyter Notebook, and I shared in the chat the link for this notebook that I use. That is almost the same as the one that is uploaded on GitHub. But the one on GitHub has already filled, the cells are all filled, so it is a complete exercise. But the notebook that I'm using only has few cells filled, so that we can type our own code. And feel free, and I encourage you to also type code when I'm typing it. And if you have any questions, issues, feel free to ask in chat or Q&A, and I will immediately answer because I can see if you type in something. And I hope that these external links that I sent in chat work. So you can also see the code that I'm having right now on the screen. So we will start immediately with importing the necessary libraries. We will be again using Python libraries called pandas and NumPy. And NumPy is here only because of the it is a prerequisite for pandas. So as in previous workshops, we will make a data set first by creating a Python dictionary, and then from that dictionary we will call the data frame method, or we will call the constructor of data frame class to pass the Python dictionary to create a data frame. And I don't want to remind too much about what we have already learned, but I will just briefly mention that data frame actually represents a data set. So in pandas, we work with data sets in the form of a data frame. So the Python dictionary only contains here two columns to make it short and easy to understand. And those columns are day and temperature. So the dataset actually represents the measurements of temperature, outside temperatures measured in some weather station for days. And we have 10 measurements because I made a pandas data range starting from 1st of July until 10th of the July. So we have 10 days. And for each day, we have some temperature measurement. So there are 10 temperature measurements, and we can pass that data dictionary to a data frame, and then just print the data frame so we can see how does it look. So it has, as I said already, 10 rows, only 2 columns. Each row represents one particular day, and each day has some temperature measurement. So we now see the whole data set, and we can discuss whether this data set has some outliers. The discussion can vary from person to person. So maybe one of you can say, okay, here I notice some temperature is outlier, some most are not. Maybe you can say, for example, that this 39.5 looks unusual, as I noted it down, because it is quite larger than most of the temperature. But it just may seem so. It may not be outlier in the sense that this is an error. For example, maybe the 8th of the July indeed had the temperature of 39, almost 40 degrees Celsius. This is not so strange in this month, but our goal is to objectively determine whether this value is an outlier, or maybe it is not, or maybe some other value. For example, in the opposite range, maybe some lower value is outlier, but we don't see so many such value that is significantly lower than others. Okay, so this is a data set, and let's say that we are not weather experts on air quality, climate, or anything like similar. We are not coming from this field. We are only maybe statisticians, programmers, data scientists, and so on. We want to, without the domain knowledge, determine is there an outlier in a data set. Okay, so the first thing before using these some of these techniques is to describe a data set, and we also learned about that in this previous workshop. So I just left a field code here so that we can just immediately run it. So describing just yields descriptive statistics of your dataset. So dataset has 10 rows, and we can see what is the average value, and we can see what is the median value. Just to remind ourselves, can someone from the chat type what is the median value here? Because we don't see explicitly stated the word median, but what value should be the median value here? Okay, Mia wrote 24.85. Okay, so, and Susan also wrote 50%. Yes, the median value is here the value that is larger and also smaller than lower than 50% of the other data, so that is correct. So this is a median value, and this is average value. We can see that average value is slightly higher, and I don't know if you know any statistics or anything about distributions, but every time you can you see that average is higher and noticeably higher than a median, then you can suspect that the distribution of data is slightly skewed, and then you can immediately suspect, oh, maybe there is an outlier in the data that skew my data, because median should not be so sensitive to outliers, while the average is. And we can see that the average is higher than median. So this is the maybe the first initial thing that we can do. So describe data and see, okay, what is the relation between average value and median value? If the average value is significantly higher or lower, that you can derive, or you may suspect that there might be an outlier that skew your distribution. Okay, so we can see that the maximum value is indeed that 39, while the minimum is 24. And why we did those this describing? So as I already said, we wanted to see the difference between the mean and median value, and also see what is the standard deviation and overall range of data. Okay, now we have some basic statistical measurements about our data, and we know a little bit more about our data, so we can also see how does it look like sorted. So if we apply sort values method on a data frame and sort it by only column that we have, and that is the temperature, in ascending manner, so we can see what are those values. So we are having values, temperature values from starting from 24 all up to 39. Okay, so maybe we just supported our suspicion that we had by inspecting the data. And I just want to remind you, every time we every time we do something like that, so every time we do the method describe, maybe it looks like it is not relevant, or we shouldn't do that to make some conclusion about data, but you always have to remember that your data will be quite larger than this data that we are using now. So it is very rare that you will have a data frame composed of only 10 rows. And if it only has 10 rows, you can just see all these 10 rows and immediately see everything about your data. But in real world, you will presumably have hundreds or thousands of rows. So you cannot, or you will spend a lot of time inspecting row by row. So this is the main reason why we use this method describe. So by using it, we can see basic statistics about our data. And also, if we now suspect after this describing that we have some outliers, we can sort our values to see what, how does this the largest values correspond or compare to other data. Okay, so the next step is using domain knowledge, if we have any. And that is the most often the uh, breaking point where if you don't have any domain knowledge, you have to just stick to the method that we'll use later. But if you have any domain knowledge, maybe it's best to use it. So if you know that the temperature of 39 degrees Celsius is suspicious, or maybe it's not even possible, it's not measured in your climate, in your area, in your city, or in your room, then you can determine or decide, okay, this value is not valid value, and I should do something about this value. But if you know, for example, okay, this value is realistic, it is quite hot when it's 39, but it's realistic, it's maybe happened before, this is the real value, I should keep it because otherwise I'm not using all measured data. So this is the first thing that you should do. If you have some domain knowledge, or you maybe know somebody or collaborates with somebody that has this domain knowledge, and that person can then guide you and say, okay, these values may seem high or may seem low, but these are not really outliers. These are okay, not so frequent, but realistic values. Okay, if you do not have any domain knowledge, then you can either use z-score detection or interquartile method that we'll learn about it right now. So z-score method, a simple idea is to measure how far a value is from the mean in units of standard deviation. So this is again one of the reasons why we already inspected our data using describe method is to learn what is the mean value and what is the standard deviation, to know those values before we perform the z-score detection. So the idea is to determine how many units of standard deviation is that value far from mean value. And if one value is has, for example, percentage of standard deviation, or maybe one of standard deviation is differentiate from the mean value, then perhaps that value is not really an outlier. But let's say that this value differentiates between the average value more than 2 or 3 standard deviation, then using this z-score detection method will proclaim it as an outlier. But this threshold is just a default value, so for example 2 or 3, but you can decide on your own what threshold do you want to use. But again, if you don't have any domain knowledge, perhaps it's best to stick to some default values. But let's first calculate this z-score, and after that we will do some filtering on a data frame to see what values in dataset differentiate between average value more than 2 or 3 standard deviations. So the first thing is to calculate the mean, and the second is to calculate standard deviation. So then we can call some temperature mean, some variable mean temperature, and then we will just call a data frame, and on the column temperature, that is the only column that we have, we will call the method mean. So how did we calculate mean right now? On the temperature column in a data frame, we call a mean function. If you are not 100% sure, you can immediately write down this temperature below the first row, and then just run this code, and you will see this is a float value, and it is a value of 28 point something, so around 28 degrees. The second thing is to calculate standard deviation. We'll calculate in a similar manner. So we will again call a temperature column, but this time we will not use mean method, but standard deviation. Again, I will just print it out to make sure that we calculate it correctly. Okay, so the standard deviation is around 5. Okay, and then we perhaps the best thing is to do right now is to add a new column in a data frame, and that is called a z-score. So z-score is the difference between the average value scaled by standard deviation. So how do we calculate this z-score? As I describe it right now, we will first add a new column in our data set, in our data frame, and we already learned how to do that in the first workshop. I will just briefly remind you. So in a data frame, in square brackets, we introduce a new column that didn't exist before, and call it however we want, and I called it z-score. And then I have to define on the right right side of equal operator, I have to define its value. And we will use also the mean and standard deviation that we just now calculated. And I will use also the temperature column so that we can use all rows and calculate it all at once. So it's not necessary to go row by row. We can just say, use this whole column, and I will just write it here to maybe it's easier if you see it. So I will use the whole column, temperature column, and I will subtract the values from this column and mean value. So I will use the mean temp variable. So how does this work? So each row is subtracted. So from each row, the mean temperature is subtracted. So if a row has lower value than mean, then this parenthesis will contain negative value. But if the temperature for that row is larger than mean, then this parenthesis will have a positive value. And one thing that is left is to scale this by standard deviation that we have in standard temp variable. Why we did that? Because that is the definition of z-score. So the z-score is a distance in terms of standard deviation. So we first calculate the distance between the row value and mean value and scale it down by standard temperature. So we now know how many standard deviation is that value far from the mean value. And we can also now introduce one more column that will only contain true or positive values. And we will calculate it by comparing the z-score column by some threshold. And I will use now the threshold of 2 because it is often used in practice. But as I said, you can use any threshold you want. But I will say here, okay, if a row is different from the average value more than 2 standard deviation, I will give that row in that new column value true. So that means that is an outlier, and I will call that column outlier. Okay, and it's easy to do this operation. So I will just need a new column that we now defined, and it is this z-score column. And I will just call ABS method that is absolute value. Why should we use absolute value? Does anyone have some idea? Why should we just compare it with threshold? Maybe you can write in chat. Yes, the outlier can be on either side of the mean. Okay, and if we are comparing negative value with threshold of 2, that negative value will be always lower than 2. Okay, so that will give after this comparing the result false, but the value is indeed maybe 2 or 3 standard deviation further from the mean, but on the other side. So that is the reason why we should first calculate is the z-score okay for values that are bound by example 0? I'm not sure. How do you mean? If you mean, do you mean that the real values can only be 0, or so? For example, here the temperature values can indeed be concentrations cannot be negative, but let's say that imagine that here temperature can also not be negative, but you can also have negative z scores because it's not it doesn't rely, or it's not or it does not rely on the range of actual values, because if let's imagine that you only have positive values, for example for height or weight, so it cannot be negative centimeters tall. You can also use z-score and have negative z-scores, because in some heights will be less than average height. And I'm not sure if I understood you correctly. Is that what you meant? Yes, okay. Okay, so z-score can be used in those scenarios when the your value, so your variable can only have positive values, because you will have some mean value and you will have values below mean and higher than mean. And that is the reason why we have to first calculate the absolute value here and then compare it with some threshold. And as I said, I will use the threshold of 2. And I will now print out data frame. So our data frame has now 2 new columns. That is z-score and outlier column. So the z-score column states how many standard deviation is a value far from the mean value. And for example, this first value 34.1 is 1 point something, let's say round up to 1, so 1 standard deviation further from the mean. And that makes sense because the mean value is 28 something, okay, 28 something, and standard deviation is 5 something, and 28 plus 5 is 33. Okay, and I said something, so the temperature is 1 point something standard deviation far from the mean. But mean is at 28, so for example, this second measurement, 24.5, is 0.6 standard deviation further from the mean, but in the opposite direction. So it is less than average, and this negative sign indicates that, but the absolute value is 0.63. Okay, and we can now see the z-scores for each value. And as I decided that I will use the threshold of 2 to say if you are 2 standard deviation further from the mean, then I will proclaim that value outlier. So this new column outlier calculates that, and we can see that for each row there is a value false. Only for the 7th row, where the temperature was 39.5, then that value is just slightly above 2 standard deviation higher than mean value. And if I'm still sticking to that threshold of 2, then this value is by that definition outlier. But if I, for example, increase the threshold and I decided I will use 3, so if you are 3 standard deviation further from the mean, only that you are outlier, and I run it again, I will have all false value here. So z-scores will remain the same, but when comparing these z-scores with the threshold of 3, the new column will have only false values. Okay. It is up to you what threshold should you use, and it depends on the context and on the domain. So again, if you have any domain knowledge, but you're not sure what values to use, maybe stick to those default values. For example, 2 or 3 are most common. And it makes sense if you increase it even further and use 4, 5, 6, 7, I don't know, 8, it doesn't really make sense. So if you say that some value is, I don't know, 5 standard deviation further from the mean, and it's still not an outlier, does it really make sense? Perhaps not. But maybe in some rare problem areas it does. Okay, so this is the method that is often used to determine whether you have outliers, or to proclaim what values are outliers in a data set. It is an easy method, so it basically requires of you to calculate mean value, standard deviation, and then calculates differences between real values and mean values, scale it by standard deviation, then just compare it with some threshold value. And then when you have outliers, then you have to do something about it. But before we delve into that, we will learn about one more method. Why is there need for more methods? Because this method is not perfect. This method is simple and often used, but maybe it's sensitive to the threshold choice. And if you're not sure about that threshold that you should use, maybe you can use one more method and maybe then see what does this method say. And then if those methods both agree on some value that this is outlier, then you are maybe can sleep better, and you are more sure that these are indeed outliers. And then you have to do something about those outliers. But let's first learn about this second method that is often also used, and it is called interquartile range. So let's introduce some definitions first. So first we have to say what is a quartile. Quartile represents 25 or 1/4 of your values, and we have 4 quartiles. So each variable, values from that variables can be grouped or separated into 4 quartiles. So first 25% of the data, then second 25%, third, and fourth. In the middle of that interquartile range, then you are on 50% of the data, and then that corresponds to median value. And we can also call first quartile and third quartile as medians of first of the second half of the data. So if a median is the value that is larger and at the same time lower than 50% of the data, then first quartile should be median of the first half of the data. So it is also larger and lower than 50%, but only on the first half of the data. So those values that are lower than median, and third quartile can be defined in the same manner, but only on the second half of the data. And what is interquartile range? That is actually just the difference between first quartile and the third quartile. So when we calculate this interquartile range, there are some formulas that are often used in the literature to then compare values with that interquartile range. And if the values are somewhat higher than that EQR, then the value should be proclaimed outlier. And also if it's lower than somewhat lower, I will explain it precisely what I mean by that somewhat, and then we also proclaim it as an outlier. Okay, that is the basic concept, but let's be more precise and more clear and go step by step. So the first step should be to derive from data and calculate from data first quartile and the third quartile. So Q1 and Q3. We will use the temperature column because this is the only real measurement column that we have. And pandas offer us an easy way to calculate quartile. The method is actually called quantile because you can use any number here. It doesn't necessarily have to be quartile, but if you want the first quartile, then you will have to put here 0.25. That it means first 20% of the data. But you can, using this method quantile, for example, derive whatever percentage of data you need, for example, 31 or I don't know, 72. But here we need first 25%. And for the third quartile, I will just copy the same formula and input here, instead of 25, I will input here 75. So these are first and third quartiles. And interquartile range, so EQR, is just the difference between Q3 and Q1. And I have one question brief for you. Will this interquartile range always be positive value? Do we have to use or call absolute method, absolute value method here? What do you think? Is Q3 always larger or than Q1, or at least same? So yes, that it should be larger or equal, yes, and that is the reason why the data, when quantile method is performed, then data is sorted, as we should, for example, if we are doing this by hand, we should sort data, but quantile method will sort it out for us, and then for the first quartile, we will just select first 25 of the data when they're ascending order, and Q3 should be higher or at least similar to Q1, but not lower than Q1. So EQR will always be a positive value. And now we are we have come to those formula that I talked about. So using this interquartile range in some kind of formulas, we set boundaries for what should be a maximal, let's say, theoretical value for our variable, or and also what should be a minimum theoretical value for our variable, and any values that are below that minimal or outside that maximum value are then outliers. And the formulas are present, and some people already devised them, so we just use them. And the formulas actually calculates so lower bound and upper bound of your variable. And the definition for a lower bound is the value that is 1.5 interquartile ranges below first quartile. So you use first quartile and subtract the 1.5 interquartile range. So you go 1 interquartile range and half below the first quartile. And that should be a theoretical lower bound for your variable. So theoretical minimum value for your variable. In the same manner, upper bound should be Q3 plus 1.5 times EQR. So similar idea, you go 1.5 interquartile range above the third quartile. And that actually represents a theoretical maximum value for your variable. And now, if any value is below lower bound or higher than upper bound, it is automatically an outlier. That is how this method works. So we will again introduce new column, and we will call it also outlier, but I cannot use the same identical name as before, so I will call it outlier EQR. Maybe I should wrote before z-score or something like that. But this column will be determined in similar fashion like in a z-score method. We will just adjust it. So as I've said, we need to compare, is the temperature value below lower bound, or perhaps it is so we not have to, okay, this is okay, or it is larger than higher bound, upper bound. Then this whole phrase will yield either true or false values. It can be either true or false. So it is true if either of this condition is true. They cannot be at the same time true. So one value cannot be less than lower bound and higher than upper bound, but one should be true to make this whole code true. And we can now just print out new data frame. Okay. Wait. We did not print out lower bound, so we can print it just to see, and also interquartile ranges to see what are those values. I will print it in prints just. Okay. Let's see. What are the values? Okay. So by using this method, interquartile range, we get first quartile is 24 something, third quartile is 31 something, and difference between them is 7.2. So when we introduce that 7.2 into these formulas for lower and upper bound, we now get the following values: 13.8 something and 42 point something. And if we have values below this lower and this upper value, then those values are indeed outliers, at least correspond, at least based on this outlier interquartile range method. So we don't have any values like this in a data frame. So this new column will give false value for each value, and then we will not have any outlier value in a data frame. And also interesting thing when we are talking about interquartals, maybe you sometime seen box plot, which is a very famous plot. And I know we still didn't learn anything about data visualization. That is the idea for the following workshops. But as we are speaking now of interquartile ranges and outliers, I wanted to just make a brief box plot to connect something about this box plot with the things that we are talking about right now. So I will just briefly import two libraries that are used for data visualization, but again, we will learn more about it in following workshops. And I'm using matplotlib and seaborn libraries that are often used and needed to draw in Python. And this seaborn is targets more data science, and it's maybe easier to use. So I just call the boxplot method and give the whole data frame, but just say I want to calculate I want to draw a box plot for temperature. And I get a plot that looks like this. So maybe you have seen some similar plots before. So we can now connect the values that we calculated by ourselves to the values presented here. So first we have, so the full name for the box plot is actually box and whiskers plots. So this whiskers actually corresponds to upper and lower bounds. So this upper whisker is actually an upper bound, and you can see it is somewhere around 40, and this lower bound is 20. Oh, why does it not correspond to actual values? It should be, just to see if I did something wrong here. So the median value should be 24. Okay. Let's see on the box plot. The median value is, it seems like it is around 25. Okay. And first quartile should be 24 again. Okay, so median and first quartile are, as we calculated, presented here on the box plot. Third quartile is actually this upper line of box inside that is in blue. And we calculated that the upper bound is, I'm sorry, the third quartile is 31.8, and that seems correct. So I'm not sure why are these lower bounds and upper bounds presented here as maybe far from the values that we calculated. So maybe just to make sure that my formulas are correct, So interquartile range is okay. This is Q1 minus, this is Q3 plus 1.5, 1.5. It seems that is okay. Maybe Seaboard uses some other thresholds. I cannot be sure. I have to check the documentation. But usually, by the definition, maybe we have some slightly different implementation. But by definition, okay, whiskers show here min x value. Are you sure about that? Because the whole idea is that we maybe have some outliers value because we do not have them here. And if whiskers show minimum maximum value, then we will not never have outliers in a graph. And I can show you what I mean with that if I just, for example, change one number and I, for example, set a really high temperature. Let's say the first value is 54 point something, and run all the code cells in a row. Okay. Okay, now when we see the box plot, you can see this small circle above, and that actually corresponds to the value 50.444. And if you said that, Mia, you said that maximum value, the whiskers show min-max value. So the whiskers should be here on the 54 point something that I just introduced. But the whiskers actually corresponds to those upper bound, a lower bound, lower bound by definition. So those are the whiskers. And if we have some values outside those bounds, like we do have now, those values are not in the box plot or not in the box. They are outside and they are represented in form of circles, maybe small circles, and they represent outliers. So outliers are illustrated here as circles that are outside of the range. So I can also maybe introduce one really low temperature. Let's say that I have minus 24. That should also be an outlier here because it should be below lower bound. Let's see. So lower bound is again 13 point something, and we can now see the outlier here. So boxplots show us that value as an outlier, so it is below that value. So by the definition, I maybe just deviate slightly. Maybe they use some other threshold, or it is just a scaling issue because of the y-axis. By definition, box plot, so the upper value, this upper whisker correspond to upper bound, lower whisker correspond to lower bound. The box plot actually is of the size of the whole interquartile range. So EQR is the size of the blue box here. And the range between the upper bound and interquartile range is top 25% of the data, so largest. And the range that we cannot see, for example, here on this graph, because it is a very small range, below, between the whisker and the lower area of box represent the lower 25% of the data. Okay. And median is also shown here, but it is not visible because of the data that I just introduced. But the median is somewhere in the box, and it is also represented with a line, and actually corresponds to 50% of the data. Okay, so these are two techniques that we can use for determining whether there are outliers in a data frame. And when we now determine, okay, we now have outliers, so these are either circles in boxplot or values outside that z-score method. and we now know that we have them, so we have to determine what should we use, what should we do with them. So so there are multiple strategies. One strategy is do nothing, just keep it, and it's okay. We will we in that scenario we could do later modeling or use some sophisticated machine learning algorithm, but we have to remember that maybe this algorithm may be more skewed or sensitive to those outliers and maybe predict either high or low values depending on where the outlier is. We can also remove it if it's clearly an error, and that is also a legit thing to do. But we already discussed that with missing data. So if we remove data from our dataset, the dataset becomes smaller. And it's always a question of how many data we have, what is the size of our data set, and if the data set is quite large and we only have few outliers, it's okay, then we can remove them. The third option is to replace it with not a number. Why? Because when we proclaim those values as nonce or not a numbers, then they are handled in an identical way as missing values. So that third option is to just treat them identical as missing values. That is also okay option, maybe even the best one if you already know what to do with missing values. So maybe you already sorted that out and decided that you will interpolate or use some substitution value or something like that. So for example, maybe it's best to do that also with outliers. And the fourth option that is also easy, but maybe can be, let's say, a bit dangerous, is to cap outliers to a reasonable threshold. So, for example, let's say that you only accept temperature values up to 35 degrees, and if you have any temperature value above 35, you will also call it. You will also proclaim it 35. So that can be also a legitimate way of dealing with outliers, but you have to decide what is the best option for you. So in this workshop, we have some practice that we can use to learn more or apply these methods that we talked about here. But I will leave that to you, and I will jump up right to the next workshop. But before that, I see that Mia also wrote something, so I will just read it. So the whiskers extend to the absolute lowest and highest data points that still fall inside the upper and lower fences. They don't just end at the fence line as less. Okay, that makes sense. So that if if we have outliers, okay, thank you. So if we have outliers, then whiskers will be by the definition upper and lower bounds. But if we do not have them, then that means that these whiskers will be just skew a bit to actually correspond to the minimum maximum values in a data frame that are inside the lower and upper bound range. Okay, thank you. Okay, and does anyone else have any question before we move on? No? Okay. So I will just briefly also introduce the next topic for today's workshop, and that is times-based indexing. So we will just delve into it, but in the following workshop that we will have, I don't know, after vacation, maybe in late August or something like that, and then we will learn more about data visualization. And in that workshop, we will learn about the libraries that I just used to draw a box plot, and we will do a bunch of different plots and see how can we customize the plots. But before that, we can also mention the one particular format of data set that is organized in, let's say, time. So time-based data frames. So in some scenarios or some real-world problems, data comes in various points in time, and we call that data like time series, and it's often the case in our environmental and sensor-based measurements that often come with timestamps. And then you have to adjust your data preprocessing and data analysis to take that into account. So we will now just introduce how do these data frames look like, what is the difference with the, we'll say, default or more simpler data sets, and what should we have in mind when dealing with those data frames. And so again, in this, I will just share it so you can see, have the same notebook. But this notebook is also uploaded on GitHub. Okay. My computer seems to be slow a bit, so maybe I can turn off camera. Okay, give me a moment. It seems that this sharing lags a bit, so I will. Okay, now it works. Okay, I paste the link in the chat, so you can follow along and use this blank notebook. So again, we will make data frames directly within the code. So I will make two different data frames that are called temperature and humidity data frames. And then as they are called, so they actually represent just temperature and humidity values at different points in time. So these are all measurement and in the same day, so 1st of August, but in different times. So midnight, 1, 2, 3, and also it is like that in the second data frame. Those both data frames are really simple. They only have 4 rows, and the timestamps are identical. So we now know, we can now see that our data frame has one column that actually represent timestamps, but they are now initially, when you upload such data set from, I don't know, internet, or you obtain it via a Google Drive, mail, or some other form, you somehow acquired it and upload it, it will initially be in form of strings. So that column will be string column, and you cannot do any kind of indexing if you have only string values. So the first step is just to convert those indexes, those columns, to special data format in Python or in Pandas that is called date time. And it's easy to do that. So the thing, how do we actually usually do it? So we just call that data frame and that particular data column, and in this case it is a temperature column. Okay, temperature column, and call pandas method to date time to date time, and again pass the same column. So that means that the new column or the existing column temperature will now be as converted to new date time format, but it will also still have the same values, but those values will not be string anymore. There will be date time values. So there will be timestamps, and it's necessary to do that so you can do some indexing after that. And I will also use that for humidity. I will just write humidity instead of temperature here and run the code. The code will not produce any output right now because I did not I first have to run the previous code cells because I didn't run them, so I don't have actual temperature df in the form of a variable yet. So in Jupyter Notebook, as you may already concluded, it matters in what order you run the cells. So I will first have to run these two code cells and then this code cell. And then this yields no error. So we can print out one of these data frames to see what is the difference. I'm sorry, I just by default use here timestamp temperature, but I have to use the timestamp. I'm talking and writing at the same time, and that may yield to some errors. So of course the temperature, it doesn't make sense to convert temperature and humidity values to timestamp, but it does make sense to convert actual timestamp values to the timestamp format. So if you inspect this data set and this data set, it doesn't make any difference if you just look at it, but it has the difference is that this value is string and this value is not string. So you can do some time-based indexing with this value, but you couldn't do that with this value. So this is the like prerequisite to before doing anything with time series. So converting to date time. After that often what is the useful thing to do is set a time-based index that makes many operation easier and more natural. And that means that we eliminate those indexes 0, 1, 2, 3, and so on, and just proclaim these timestamp value as indexes. So you perhaps learn about, I think you did, about the indexes in Python in general, and you know that indexes are the values that are used to identify something. So you cannot have multiple values on the same index, and you also cannot have multiple values for the same timestamp. At least in this scenario, at least for that temperature and humidity data frames. So it does make sense to use these timestamps as indexes. and we will just proclaim these columns as indexes, and these columns will be now indexes and not these ones. So we will now have timestamp index and temperature values. Again, this is not a hard thing to do in pandas. We just call our data frame and proclaim new data frame with new formats. So we say, okay, the new temperature data frame will be similar as the previous one, but with the index set on timestamp column. And we will also do that with humidity. Okay, if I run it, I get just a green error, no error, but I can print out humidity. Okay, and we can now see the difference. So there are no more integer indexes, and timestamp are actually indexes that are used to identify the humidity values here in humidity data frame. So when the index contains timestamps, we can now filter by time using intuitive syntax. I'm sorry. So filtering by time now becomes much easier, because if you want to, for example, look what happened at that date and that particular time, you can now just call your data frame and the method lock, as we discussed. We learned about that method in first workshop, that is used to locate, but you have to provide some index to that method. And you can now just say, okay, I want to know what was the temperature on August 1st at 1 o'clock. And it will say, okay, the temperature was 20.4. You cannot do that before when the timestamp was not an index, or you could do that, but perhaps not so easy. And this is just intuitive, so you don't have to be code monkey or programming expert, but you can now just use intuitive, simple method that we already learned. For example, locate. So you just locate and use the index, as we converted timestamps to indexes. Okay, you can also do it in a form of a range. For example, you want to filter out all temperature values between 1 and 4 o'clock. So you now get 3 values, because only 3 values are in that range, 1, 2, and 3. So you get 3 temperature values. You can now play with these ranges, or you can use multiple ranges, one value particular, whatever you prefer. Now when the timestamp is also index, we can do sorting by time. So time-based operation works best when the index is in chronological order, and sorting becomes much easier. So you just have to call a method that is called sort index, and you just have to write in what order are you sorting, so in ascending or descending. But indexes correspond to timestamp, and let's say that I want to, for example, have different order. I can just write called temper, okay, sort index, and see what will happen. Just okay, so now it's sorted a normal way that is expected from that method, but we can do it in some other way. So for example, that we want to sort in different order, we will just call ascending is equal to false, and we will get timestamps from 3 to 1. Okay, this is one more reason why we converted timestamps into indexes, so we can do filtering and sorting much easier. And also one, maybe even last thing to do is to join measurement from these different sources, and this is actually the main reason why we converted the timestamp into indexes is when you have multiple data frames with similar timestamps. For example, like we have here, we have temperature data frame and humidity data frame. So these are two different data frames that consists of temperature and humidity values. But let's say that we want to combine them or join them into one more comprehensive data frame, and we want to have for each timestamp both temperature and humidity values, but mapped, not in some random order, especially not in the sense that, for example, you have temperature value for that timestamp and humidity value for some other timestamp. And when both data sets are formulated in a way that the timestamps are in the form of indexes, this becomes much easier. So you can now just call the join method on one of those data frames and pass to the join method the other data frame and produce the third, let's call it combined data frame. So I will call it combined df, and on the first, that is temperature the data frame, I will just call join and pass the other one, so humidity. And I will put also this parameter, but I will explain it a bit later. So let's first run the code and print this combined data frame. Okay, so the combined data frame now has two columns, temperature and humidity, and the values for timestamps are mapped. So we have temperature value for the timestamps 00, that is midnight, and also humidity value for that particular timestamp, and also for other timestamps. The one parameter that we used here is called how, and I set it to inner, and that means that if these two data frames have different ranges of indexes, only the intersection of those two data frames will be in a combined data frame. So, for example, if temperature has some timestamps and humidity does not have those timestamps, they will be removed from the combined data frame. It is also case in the opposite situation where humidity, for example, if humidity data frame would have some timestamps that are not in a temperature data frame, and I stated that I want inner join, so that means intersection, the combined data frame will not have those timestamps. There are other forms of joining. If I state outer join, then all timestamps will be present here. But this will not change the situation here because these two data frames have almost, they do have identical timestamps. So let's just change this a bit. There is actually no difference here. Okay, so because just to make sure that I state this correctly, so the question is, what is the difference between join and merge? Okay, just to show you maybe with example first, and maybe it will be easier to understand it like that. So let's say that I introduce one more value with a different timestamp. Let's leave it the same day, but let's say 4 o'clock. And also in humidity, I will put one more value. So let's say 5. Okay. And I will run all these code cells. Okay, this will take a bit of time. I have to also introduce one temperature. Okay, so we now have temperature and humidity with 5 different rows, but the time steps are not identical because I introduced time steps 4 o'clock and 5 o'clock in temperature and humidity, but these values differ. And now when I do join, okay, and if I leave it inner, so combined data frame will only have again these 4 that overlap. But if I leave outer join, then the combined data frame will have all these values. So what happens with the humidity value for time step that is only present in temperature? Then this value becomes none, not a number. And this is also case in the temperature. For a temperature when having timestamp that is present in humidity data frame but is not present in temperature data frame. So this is let's say disadvantage of outer join. The advantage is that you have more values, so all values, but some values are not present. Also, we have left join, where we will only have timestamps from the temperature data frame because he is on the left side of the join, and we also have right join where we have only timestamps of humidity because he's on it is on the right side of join. So the difference between join and merge is not maybe straightforward here, because if we think about it in the sense of joining of this parameter how, because merge also has how parameter, but the difference is actually whether you are combining on a row level or a column level. So merge actually finds the identical column between the two data frames and merges the data frames based on that column. So let's say that you have, I don't know, a data set with some countries and some information about those countries, how many inhabitants are, what is the language, and let's BDP or something like that. And then you have one column that is called country name. And that, let's say that you have one other data frame that also has some information about countries, but some other kind of information. And you want to combine all those information into one data frame. Then the combined data frame will match on that column country name. So these two data frames have to have one shared column name, and that in that case this is country name, and this is just merging. And joining is just stacking columns together, where you don't have to have identical columns, but what you should have is identical rows. So the joining is done on a row level, whereas merging is done on the column level. Okay, and this is the also one thing that I wanted to show you, how to join measurements from different sources. And we also have some slight, let's say, exercises to do that, but maybe because of time and also we also learn today a bunch of stuff. Maybe I can leave that to for the next workshop, because in the next workshop we will introduce, as I said, visualization methods, and this resampling and filling gaps, aligning datasets with different timestamps actually are perfect fit for that next workshop, where we, as I prepared here, you can see we discuss the visualization part of time series, not only time series, but in general. So, okay, we can, if you agree, conclude with this joining. So we, in this workshop, really quickly went through the data sets where we have timestamps, and they should differ at least in some to some degree to classical data frames, because timestamps in this scenario actually should be formulated as indexes. So it should be represented as indexes. And when we concluded and actually do that, then we can do filtering, sorting, and joining much easier using methods that we already learned in previous workshops. But the main prerequisite is to set the timestamps as indexes. After that, aligning, resampling, visualization, and something that we didn't do today, we didn't speak about it today, it will also become easier. But I will again repeat it. So the prerequisite is to format timestamps as indexes. Okay. Are there any questions regarding either this time-based indexing or outlier detection? Or are there any comments? Or maybe you can write something that you expected to hear about today, but we did not have time to discuss it, so maybe I can prepare it for the next time. Because there are a bunch of things that can be discussed both in outlier detection and time-based indexing, but these workshops are not meant to last longer than 2 hours. So I have to decide what is maybe most often used and maybe most useful to learn. So we already passed through that content, and maybe there are a few exercises that are not so either often employed or are there any libraries that enable fast implementation? I'm not sure in what sense that you mean fast implementation of what. Of often used methods for outlier detection removal. So this pandas actually is really easy and straightforward to use, because you can just derive mean, for example, for z-score, mean, standard deviation, and just do that sort of filtering. But you have to write at least 2 or 3 lines of code. I think that today's graphical tools that are used for data analysis stemming from Excel and R and also, I don't know, Keel or some other tools do have those methods integrated, but because those are state-of-the-art methods, as myself, I use mostly Python because I just write programs, write scripts, so it's not so hard for me to do that. So I cannot really on the top of my head name more tools that I named that enable even faster implementation of those methods, but I can check it out and maybe write it at the beginning of the next workshop, or if you want to, I don't know, this directly contact me via email, I can explore it further and return to you. So maybe write name a couple more similar tools.